In the spring of 1935, Albert Einstein launched a highly structured campaign against the core tenets of the new quantum mechanics. We see the documentation of this effort in the archives of the Physical Review. He refused to accept a universe governed by chance. To Einstein, valid physical laws required strict causality, and a theory relying on probability was unacceptable. In May, he published the EPR paper, co-authored with Boris Podolsky and Nathan Rosen. The text aimed to prove mathematically that quantum mechanics provided an incomplete description of reality. Weeks later, in July, Einstein and Rosen published a second paper. This one attempted to solve the particle problem within the mathematical framework of general relativity. These papers address different physical domains. One dissects the behavior of entangled quantum states, while the other models the macrogeometry of spacetime. Einstein coordinated these releases to build a singular defense of determinism, attacking the foundations of uncertainty from two sides at once. The foundation of Einstein's argument rests on a principle called local realism. Local realism asserts that spatially isolated systems are completely described by their local properties alone. Under this rule, objects possess definitive, pre-existing values for their physical properties prior to any measurement being made. Quantum mechanics proposes the exact opposite. Properties like position and momentum remain probabilistic distributions until the specific moment of observation forces them into a definitive state. If local realism holds, the probabilistic math of quantum mechanics is an incomplete placeholder for a deeper, more rigid set of physical laws. General relativity described gravity as a continuous field, but it was plagued by mathematical singularities, points of infinite density, like the Schwarzschild singularity. To Einstein, singularities represented a breakdown in a complete deterministic field theory. To remove this infinite point, Einstein and Rosen introduced a mathematical coordinate substitution, setting u squared equal to r minus 2m. This embedding diagram shows the geometry. Eliminating the singularity created a continuous, finite tube connecting two flat sheets of spacetime, Einstein's model for a neutron. To account for charged particles, they scaled the model, requiring two parallel bridges connecting the same sheets. Here, the model hit a mathematical roadblock. Accounting for the many-body problem of multiple interacting particles meant introducing multiple parallel bridges, which caused the theoretical flat sheets of spacetime to become hopelessly congested. Einstein eventually abandoned the effort, but his intent remains clear. He did not invent ER bridges to explain quantum entanglement. He invented them to replace quantum mechanics with deterministic topological geometry. The EPR paper approached the same goal from a different angle. It proposed a thought experiment. Two particles, A and B, interact with each other and then separate indefinitely. Einstein defined an element of reality with a specific criterion. If you can predict a property with 100% certainty without disturbing the system in any way, that property physically exists. Because the particles interacted, their properties are correlated. Measuring particle A's momentum allows us to instantly infer particle B's momentum via the conservation laws, without ever touching particle B. Einstein then introduced the famous separation hypothesis. Because the particles are separated and no longer interact, the act of measuring A cannot physically cause a real change in B. Quantum mechanics states that you cannot simultaneously know the precise position and momentum of a particle. Yet, in this setup, both can be inferred for particle B without measurement. Therefore, the theory fails to capture existing information. For Einstein, the EPR paradox was absolute proof. Quantum wave functions were incomplete descriptions of a universe that was locally real and strictly deterministic. Decades later, theoretical physicist John Bell formulated a mathematical inequality to test Einstein's claims. Today, this is evaluated through rigorous experiments testing the threshold of quantum steering. To definitively disprove local realism, an experiment must close three massive physical loopholes: the locality loophole, the freedom of choice loophole, and the fair sampling loophole. In 2011, Whitman and colleagues constructed an experiment to do exactly this. This floor plan details their setup. with a 48-meter physical separation between Alice and Bob's testing laboratories. This Minkowski diagram charts the experiment's intersecting light cones to verify causal independence. The orange region isolates Bob's setting choice from Alice. The blue region isolates Alice's report from Bob's measurement. Their intersection creates a green 75 nanosecond trusted window, isolated from subluminal signaling. The experimental result yielded a steering value of 1.049. This violates the mathematical limits of local realism by over 20 standard deviations. With all three major loopholes closed, the data excludes the class of local realistic theories Einstein championed. We are left with a universe where non-locality is a measured fact. While Einstein's attack on quantum mechanics failed, his geometric model from the ER paper experienced an unexpected afterlife. After Einstein's death, physicist John Archibald Wheeler resurrected the ER bridge mathematics and rebranded the structure. Wheeler modified the original concept. This diagram illustrates Wheeler's two-mouth wormhole, where mouths P1 and P2 connect distant points across the exact same space-time surface A, theoretically allowing for instantaneous traversal. Wheeler took Einstein's mathematical tool, designed to enforce strict local determinism, and mutated it into a theoretical mechanism for instantaneous, non-local travel. Today, the frontier of theoretical physics focuses on reconciling quantum mechanics with general relativity, often utilizing conformal field theory. Within this framework, physicists Leonard Susskind and Juan Maldacena proposed a concept known as the ER equals EPR conjecture. The premise centers on creating maximally entangled EPR pairs of black holes within an anti-de Sitter space. This Penrose diagram displays the resulting geometry, with the left and right exterior regions connected by an interior ER bridge. Susskind and Maldacena identified a mathematical duality. Quantum entanglement of an EPR pair is equivalent to the physical geometry of the ER bridge connecting them. This equivalence does not suggest that quantum states signal each other faster than light. It implies that entanglement itself generates the spatial connectivity of the universe. Einstein failed to dismantle quantum mechanics, but in his attempt to build a deterministic geometric alternative, he accidentally provided the exact mathematical map required to understand the entanglement he so deeply opposed.